Hello everyone, welcome to this edition of our Cassandra Community webinar series. I'm delighted today for this Cassandra Internals webinar to have with us Aaron Morton. Aaron Morton has done several webinars for us, and he actually presented at the Cassandra Summit two fantastic presentations. One in case of emergency, break glass, and that will be coming up on the 29th, so do not miss that one. And then this one, Cassandra Internals. And just a little bit of housekeeping before I turn over to Aaron. Aaron will be taking questions at the end of today's session. So if you have a question for Aaron, please use the Q&A tab here inside of WebEx. Type your question in there, and I will read it out at the end. And Aaron, congratulations. The Last Pickle, which is your consulting organization, I believe, is expanding. Before you get started, just tell us a little bit about that and a little plug for the community.
Thanks, Christian. Yeah, I've been working as a freelance Cassandra consultant now for, I think, 2.5 years. And, you know, the community's growing a lot. The product's growing a lot. And the interest in Cassandra has grown a lot over that time. So I've gotten together with someone else who's been in the community for 3+ years, Nate McCall, a former DataStax staffer. And we're now working together under the brand The Last Pickle, which has been my crazy email domain for the last few years. We work together to help clients deliver and improve on Apache Cassandra solutions. I'm a committer on Cassandra. Nate and I are both DataStax MVPs for Cassandra. He's the maintainer of the Hector Java library. Together we have 6 or 7 years experience with Cassandra. We're based in Wellington, New Zealand, and Austin, Texas. So with that out of the way, what we're going to talk about today are Cassandra internals. Now, obviously, it's a very complex code base. It solves some complicated problems, and we've only got a small amount of time. So we're not going to get into the nitty-gritty details. Instead, we'll look at some of the key areas of the code base, some of the important classes, some of the places where exceptions or timeouts that you see as a client consuming Cassandra services get. So we'll skip past our first slide of About Us because we've just been through that. So we'll start by looking at architecture, and then we'll move on to look at some examples from the code base. Architecture-wise, we can draw a very simple diagram. There are some clients. They connect through APIs. Those APIs talk to some software components that we'll call cluster aware. They talk to software components that we'll call cluster unaware. And those cluster unaware components talk to disk. They take things from memory, put it on disk, take things from disk, put it in memory. And when we put this stack together in a cluster, as you'd expect, the cluster aware components talk to each other, and the cluster unaware components continue just doing their work of reading and writing from disk. I think we can put some better labels on this diagram, though. Cassandra is an Amazon Dynamo-based system, so we can call our cluster-aware components the Dynamo layer. We can call our cluster-unaware components the database layer. At its heart, Cassandra is just a very fast log-structured storage engine, and all that database layer does, take things from memory, put it on disk, take things from disk, put it in memory. The Dynamo layer takes things from memory on individual machines and brings that together on one machine, handles issues around consistency, and makes those results available to the API that takes it back to your client. Let's expand our agenda for today. We'll talk about the API layer, then the Dynamo layer, and then the database layer. We'll break the API up into transports and services. Transports, we have 2 now as of version 1.2. We have our Thrift implementation. It's been there since day 0. Of course, Apache Thrift came out of Facebook in the same way that Cassandra came out of Facebook. we have a couple of implementations of the Thrift server. The one that's selected is controlled by the RPC server type YAML configuration setting, and the default sync server is the custom T thread pool server. This guy uses a thread pool. Each thread is associated with a client connection. It lives with that client connection for the life of that connection. Once the client disconnects, it goes on, works for another client. And we have a custom implementation here because there's some cleanup tasks we want to do when the client disconnects. You may see in the code base the custom T non-blocking server. That's deprecated, so we won't talk about that guy today, but you might see it. The other one that we have is the custom T HSHA server, half sync, half async server. So this uses a thread pool like the T thread pool server, but each thread processes one request response from a client and then goes on to process another request potentially from a different client. So we use less threads on the server side. On to now the native binary transport. Now this is new in Cassandra 1.2. It was beta there. It's actually coded in the Cassandra code base, unlike the Thrift server, which was a package that we bring in. It uses Netty under the hood. Initially in version 1.2, it was disabled by default. You'd start it with the Start Native Transport YAML configuration. You can run both Thrift and native binary transports. At the same time, native binary uses port 9042. The native binary transport code starts and lives in a package called transport. When in these slides where I have OAC, I'm talking about a Java class package, org, Apache Cassandra transport. We look at the server class. This is where we set up our native binary server. First thing we do is we set up an execution handler. This is our thread pool. This uses threads in the same way the HSHA server does. It has one thread that processes the request from a client, returns the result, that goes on and processes a request from a different client. To do that, we do select on the sockets, so we use Java NIO to do that. That's the NIO server factory channel. And then it sets up this thing in Netty called the pipeline. And the pipeline is a series of stages that your request goes through, and then the response comes back out. So those stages are things like frame encoding and decoding, message encoding and decoding, compression and decompression, all the way up to a stage in the pipeline called the dispatcher. And the dispatcher in our code base is in a class called message.dispatcher, and it has a very simple function here called message received. This is called with our new message from the client. We take our server connection state and we validate that this message makes sense. So if we're already authenticated, we don't expect to get a credentials message from the client. Once that's passed, we execute the request, and that gives us a response that we can send back to the client later. But before we do that, we get the connection state again and check to see if we should apply a state transition. For example, if we've got credentials and we're now authenticated, we move into an authenticated state. Once we've done that, we write the result back to the client. Now, all the messages that the native binary transport processes are defined in a protocol document. This is a human-readable document. It lives in the code base. If you want to get an idea about how it works, it's a great place to start. Up a little bit higher now into our API services. Let's start with JMX. JMX, the Java Management Extensions, is a great way to understand what Cassandra is doing. It's implemented as a series of management beans. These management beans are spread around the code base, but they all implement interfaces that end with mbean. So they're very easy to find, and I'd say almost all of those interface definitions have very good documentation about what they do. They're implemented in a very sensible way. For example, there's an interface called storage proxy mbean. It's implemented on the storage proxy class, and it's exposed under JMX as org Apache Cassandra DB type equals storage proxy. Very easy to locate. Thrift works both at the transport layer and at the services layer. The services layer, Thrift implements the RPC interface that we've always had and we had before CQL3. It's implemented in one class called Cassandra Server. This guy does what you'd expect. It has access control on it, it has input validation, and it maps to and from the Thrift types to the internal types because we don't use Thrift types internally. That Thrift interface is defined in an interface definition language file, lives in the code base. It's not particularly a human-readable document, but if you go and have a look, you'll get a feel for all of the things that are available on the RPC interface. This is the interface that's used by clients such as Picasa, Hector, Astianix, things like that. Probably one of the more popular calls on this Thrift interface is getSlice. This is where we want to get either some named columns or a slice of columns for one particular row. It's implemented in a function called getSlice on Cassandra Server. This code example here is from version 1.2, so the first thing it does is it sets up request tracing and then gets the client connection state. We have this for both Thrift and CQL3, and we do some basic access controls. Do you have permission to read from this column family? Once we pass that, we've got to now go through some abstractions because reading columns from a row is a pretty common approach, a pretty common function in Cassandra. So we jump into multi-get-slice internal. In multi-get-slice internal, we do some validation of your request. Have you asked us to return -1 columns, things like that. And we create some objects called read commands. These are internal objects that represent your request. These are something we can execute. We pass those on to another abstraction called getSlice. In getSlice, we can see here the API starting to merge into the next layer, into the Dynamo layer. getSlice takes read commands, which are internal, and returns Thrift types, which are external. To get the results, it calls read column family, and this is where your Thrift API call ends. In read column family, we take read commands, we pass those to a class called the storage proxy, and we return back the internal representation of those results. So if that's where our Thrift call ends, let's have a look at CQL3. The equivalent of the Cassandra server is called the query processor in the OAC CQL3 package. This guy takes care of preparing and executing CQL statements. It's used by both Thrift and native. So native transport only uses CQL3, and on Thrift we've got execute CQL3, calls to that on the Cassandra server class end up over here in the query processor. Again, does the things you'd expect, has access control and input validation, and it returns transport messages from our transport package that we saw before in the native binary package. Our CQL3 grammar is defined in an ANTLR document, lives in the code base. Again, not particularly written for humans, but you can certainly go and have a look and get a feel for the breadth of the CQL3 language. All of the statements in CQL3 are implemented in a two-phase approach in the code base. First, we generate things we call parse statements, and these are created by the ANTLR compiler. They're essentially a representation of the request that you've sent to the server. It has a couple of other things, like it tracks the bound term counts when we're using prepared statements, but it has a function on it called prepare that we call to create the actual CQL statement. And this is the thing that we can execute. Again, some things you might expect. We want to do access control and we want to do validation. Do you have permission to delete on this column family? We've got an execute function here that gives away a few hints about how these CQL statements are used. We can pass in a consistency level. We can pass in variables. We've got some state that we pass in. So these things can get reused. These can be our prepared statements. And when we look at the select statement, probably the most complicated and most popular statement in any data language, our prepared statement is defined in in an internal class called raw statement, has a lot of input validation in there, and the prepare function, creates our select statement. Again, this is the thing we can execute. And when we look at that execute function, it's very small, it creates read commands. These are the same classes that the Cassandra server created, and it passes those to the storage proxy. That's the same storage proxy that the Cassandra server uses. So our API call will come into either the custom T-thread pull server or the query processor, and or the message dispatcher, then onto the query processor or onto the Cassandra server and then the query processor. In either way, it creates read commands. Those read commands are handed down to the storage proxy, which is where we transition into the Dynamo layer of Cassandra, where we're starting to think about things in terms of a cluster. In the Dynamo layer, there's a couple of packages I put in here that we don't have time to talk about today. DHT package is the hash tree. This is where you'll find partitioners and tokens. GMS is the gossip service. Locator is where you'll find the snitch and the replication strategies. And stream is where you'll find the classes we use for anti-entropy. Now let's start with the service package. So here's our storage proxy we talked about before. This guy's the workhorse of everything we do cluster-wide. All of our storage operations for reading and writing pass through here. So it does things you'd expect. It selects endpoints that we want to do a read and write to. It checks that consistency level nodes are available. It sends messages about the read and write request to stages, and we'll look at stages shortly. It sits around and waits for a response in a very efficient way, and then it stores hints if we need to and hands the results back to the API layer. There's another important class in this package called storage service, and this guy is a wrapper for a lot of functionality that lives elsewhere. And this contains entry points for all of our ring and operations, tracking ring state, starting and stopping membership, mapping between nodes and tokens and nodes. You can imagine we do that sort of stuff a lot. So if our storage proxy uses the storage service and we want to do a read, and we work out we want to read from 3 nodes, we send off our requests, and later on, hopefully, we get back 3 results. And now we've got 3 potential different answers to the same question. And we have to have a way to resolve that and come up with one answer to give back to the client. And that logic is encapsulated in classes that implement the iResponse resolver interface. Very simple interface. We call preprocess when we've got a message from a replica. And once we've got enough messages, we call resolve. And resolve returns the result that we want to send back to the client, or throws an exception. The row digest resolver is the one that we use the first time we run the read request. The first time we run it, we ask one node for the data response, the actual data to send to the client, and we ask the other nodes just for a digest of the data they would send. In the resolve implementation, the row digest resolver calculates a digest for the data that it got, compares that to the other digests, throws a digest mismatch exception if they don't match. If they match, it just returns back the data. If we get a digest mismatch, we run the read a second time while the client's still waiting. We ask all nodes to return the data, and this time we use the row data resolver. This guy's a little bit more complicated. It uses our timestamps for the columns, and it works out the result that we want to send to the client. And then it works out which nodes have a different value than the one we want to send to the client. It works out some mutations to send to them and sends those mutations without waiting for a response so that they update their data on disk, and then returns the result back that we want to send to the client. And if we're doing a range scan, a little bit more complicated again, replicas can return back different numbers of rows, so we use the range slice response resolver. That's great on the read path. Obviously, we don't deal with that on the write path, but both the read and the write path have this common idea of a response handler or a callback. And this is an object that is an internal sink for incoming messages about your request. that implements a simple base iAsync callback. It gets called when we get a message back about this particular request that we're doing for you. And we have a nice implementation of that in a class called read callback in the service package. It has a nice little function called get. When you call get, we go in there and we wait for a condition to be set. This condition is set once we've got enough responses from the client. And it's set by calls onto our iAsync callback interface, which are coming in on a different thread to a thread that may have called this get function. It's set once we've got consistency level nodes and our data response back. If we time out waiting for it, and the timeout here is the RTC timeout, then we throw a read timeout exception. And this is where an exception that you get on the client, a timed out exception, starts in the read callback.get function. Hopefully, though, our condition is set. We pass through that. We call our resolver, and we call resolve. That gives us our result back. Hopefully, it doesn't throw an exception. And now we're on our path to sending results back to the client. So all this comes together in a function called fetch rows on the storage proxy. This guy gets called with a list of read commands. We iterate through those read commands, and we get a list of the endpoints that we want to send the request to. For each request, for each read command, we create a row digest resolver because this is the first time we're doing this read. We use the row digest resolver, some information about the consistency level and the endpoints we want to send it to, and we use that to construct our read callback. From our read command, we then create some messages, and we use those and our read callback, and we call the messaging service, which we'll look at shortly, called send RR, send request response, to send messages that the messaging service will deliver the response back into our read callback object. Again, that read callback object is specific to this particular read command, and so it knows how to deal with that. Once we've iterated through all of the read commands, we then iterate through all of the read callbacks that we created. And we call get, and in the good case, get just returns our data back, and we're off and running to send responses back to the client. But remember, it can block, and it can block for up to RPC timeout, and it can throw exceptions. If we get a digest mismatch exception, we run this particular read command a second time using our row data resolver. If we get a read timeout exception, we throw an exception that goes all the way back to the client. The glue that holds all this together is the net package. We have a messaging service class in the net package, and this implements a transport and a protocol for inter-node communication. We'll just look at the protocol now. The protocol is made up of a series of verbs, simple things that you'd expect nodes to ask each other to do. Mutation or a read, either one of those can generate a request response that comes back. If we're doing anti-entropy repair, we'll get a tree request. We'll send a tree request. We'll get a tree response back. And there's lots more, but they're the basics. And the messaging service has no idea what to do with these verbs. All it knows is there are things called verbs. Things that handle verbs are objects that implement the iVerb handler interface. So we have a map of verbs to verb handler objects. And the verb handler interface is as simple as you'd expect. Do your thing, do verb. Here's the message, here's an ID for the message. And just because we've got an object, we've got an object, but we need a thread. We need somewhere to run it. So we map our verbs onto stages. And these are the stages from the staged event-driven architecture. These are the stages that you see when you run node tool TP stats. The read stage, the mutation stage, the response stage, there's gossip stages, and all those stages that we have there. So now we've got a verb, an object that can do the verb, and a thread that we can run that object on. So we bring all that together in receive function in the messaging service class. Very simple little function. Gets called with a message. We take the message and we wrap that in our message delivery task. This is just a runnable, and we'll see this in use in a minute. We take our message type, our verb, and we use that to get a stage. And remember, the stage is just a thread pool. And then we take our message delivery task, we drop it into the stage, and then we go back and run this whole thing again. This is running on a thread that is dedicated to reading incoming messages from one particular node. So this guy just keeps pulling messages off the socket, wrapping them in delivery tasks, putting them in the appropriate thread pool, and then going back and doing that again. Later on, hopefully not too later, our message delivery task is run in the appropriate thread pool. So this thread pool could be local, it could be a thread pool on a different machine, which is more than likely is. When it runs, it looks at the time it was created. And if that time is longer than RPC timeout, it does nothing. And remember before we saw in the read callback.get function, we stop waiting after RPC timeout. So this is Cassandra implementing the CEDAR idea of load shedding. We're not going to do this work because no one else is waiting for it, so it's a waste of time. The sorts of messages that are droppable are reads and writes. We don't drop things like anti-entropy and things like that. But when you see drop messages in your no-tool TP stats or in your log, this is where they're dropped. Hopefully, though, that's not the case. So we get the verb handler, and we call do verb. So now we're running on the remote machine on the appropriate thread pool, and we're taking the verb handler object and running that. So we've now transitioned across machines. We used the API layer to understand what the request was. That got us into the Dynamo layer. In the Dynamo layer, we were able to work out what remote nodes to talk to and set up structures so that when they send responses back, we can process them. We use the messaging service to be able to send those messages, and we've seen how the verb handlers grab those messages on the other end, and typically they make calls into our database layer to do our reads and writes. Again, a couple of packages in here we won't have time to talk about today. The cache package has your key and your row cache in it. The IO package has your SS table readers and writers, and the trace package contains the request tracing that came in version 1.2. The concurrent package is pretty small, and this is where we define our stages. These are thread pools that are mapped to this enum of stages. Again, the stages you see when you do no-tool TP stats. The stage manager is a very simple class. At startup, it reads all of our config, the number of concurrent writes and concurrent reads that you have in the YAML file, the memtable flush, number of memtable flushes and things like that. Here are our stages, as we'd expect. The DB package, finally, is where we have our database. The thing that you think of as a key space is implemented in a class called table. When we're running, we have one instance of table per key space. We have a static function on there called open. We call all the time to get that key space in, to get that table instance. When we want to read some data, we call get row. When we want to write some data, we call apply. The thing that you think of as your column family or table in CQL3 is implemented in a class called column family store. If we want to do a read on this guy, we call a function called get column family. Internally, a column family is just an ordered collection of columns. And that could be an entire row. It could be part of a row that's sitting in a mem table from a write. It could be part of a row that's part of the result of a read. It's just a collection of columns. And all the action for a read happens in a function on the column family store called get top level columns. We also have an apply function here for our writes, similar functional signature to the one at the table level, except we've added on here the secondary index manager to update those things. A column family is actually a column container, and this interface has a bunch of add and remove functions on it. And in the 1.2 code base, at least, we have 2 implementations of that, column family and super column, and you get a feel now for why a lot of committers for a few years have been saying we don't like super columns too much, because there are a bunch of places in it like this where we have these additional abstractions and code branches to deal with super columns. And if you've never heard of super columns, don't worry, you're not missing anything. But we further abstract the idea of collecting columns into an interface called I-sorted columns. Bunch of add and remove functions that you'd expect, and a few different implementations here. The array back sorted columns is a thread unsafe implementation. It's very fast. It's used on the read path in places where we know that only one thread will be dealing with the collection. The atomic sorted columns is used by the mem table. And this is the guy that gives us our row level isolation through the use of a data structure called the snap tree. Our row level isolation means that if you've got a writer who's updating 50 columns on the row, readers will only ever see 0 or 50 of those columns being updated. And we have the tree map back sorted columns. This guy's a thread safe implementation that's used in places where we are not doing writes, not doing reads, but we need multi-threaded access to the collection. And finally, we have a class that has the same name as the thing that we talk about, which is the mem table. It has a put function on it to do writes. And we pass in here our key. Decorated key in the code base means it's the key and the token. The column family, so we talked about column family is just a collection of columns, and our index updater. Pass that guy in, he updates the in-memory structures. If you want to see how things get flushed to disk, you could start by looking at flush and signal on this and follow that through. And lastly, our read commands. This is where we started at the API layer. We only have 2. We have slice by names read command. This is where we want to read columns on a particular row and we know the names of the columns. Select foobar as. And we have slice from read command. This is where we want to read the first 10, 20, 30, whatever columns from a row. These guys deal with iterators, a lot of iterators. We have these disk atom filters. We use these to create iterators over mem tables. A column family can have multiple mem tables in memory at the same time. They may be sitting in the queue waiting to get flushed. Of course, we only write to one at a time. And a column family can have multiple SS tables, so we need iterators over those. We have implementations here that do things you'd expect. The names query filter is used when we have a list of column names that we want to read. The slice query filter is used when we want to get a slice of columns. The identity query filter is used when we want to read all the columns off the row. So we'd use that where we have compaction and repair and upgrade tables and things like that. Or when we're filling the row cache. If we get a miss on a column family that has row cache enabled, we go and read all the columns to fill the row cache. So what have we got here? Well, our request comes into the API layer, comes into our custom T thread pool server or our message dispatcher, goes to the query processor or to the Cassandra server and then on to the query processor. Either way, Thrift or CQL3, we create read commands that we pass to the storage proxy. The storage proxy creates response resolver to handle the responses from multiple nodes, the async callback to act as a sync for incoming messages, and uses those and the messaging service to send messages to stages. Those stages live on local and remote nodes. When we when we get to that thread pool, when we get to that stage, we use a verb handler, which understands how to process the message. On the read path, that verb handler will go and look at our table, our key space, eventually then to the column family store, which is our column family, and then into a series of iterators and things that are disk atom filters which read the results off disk. We package that up. The verb handler sends our response back. That ends up back at the messaging service at the coordinator node. The response is delivered into the iAsync callback object. Once enough responses have been received, that uses the response resolver. We get our result we want to send back. The storage proxy returns that back, and then your query processor or Cassandra server takes care of getting that back to you, the client. And that is our 35-minute deep dive on the Cassandra code base. I'd like to hand over now to Christian and any questions that you may have.
Thanks a lot, Aaron. And just a reminder, use the Q&A tab inside of WebEx to ask your question. We're already getting some coming in. So, Aaron, first one from Rudy. Is there a way for the Thrift interface to know in advance when a particular client query will use a compound keys table CQL3?
So if there's a call on the Thrift interface for CQL3, the Cassandra server just passes that through to the query processor, so it doesn't know anything about what's going to happen there. So I'd say no.
Okay, thank you very much. And Ian asks, and this is, I think this is a good one for the community, and I know the direction of CQL was a little contentious at first. So he wants to ask, where is CQL going? Are we making just another SQL engine?
So the position of CQL is that it's never going to be parallel with SQL. We won't be doing joins, we won't be doing aggregates, we won't be doing things like that. What CQL does is implement some well-known abstractions about how to store data on Cassandra in a very extensible way. The CQL protocol and the native binary protocol are more extensible than Thrift. And it provides some scaffolding that ORMs and other things like that might want so that they can interrogate and understand the schema. I think there's some arguments around, at the human level, schema at some level being useful. Certainly if you look at some data and you don't have an understanding of what's in there, that can be painful. But it's always going to be designed around reading and writing data that you know about in a fast way. So I think that they're still essentially parallel. There are a few use cases where Thrift is better than CQL3. For new users and people who are working with certain tool sets, CQL3 can be an easier decision. Performance-wise, they're mostly the same. And whenever I'm talking with clients, I explain these things. We look at some of the technical implications of how they do things, and then I say, whatever you feel like doing is the best solution. Because this is basically, if you are more productive on one than the other, and they meet your technical requirements, go with the one you're more productive on.
Thank you very much, Aaron. And yeah, that echoes what we see in the broader community as well. People who are new to Cassandra are, coming from a hallelujah, thank you for CQL. If you've been using Cassandra for a long time, then you're probably pretty immersed in Thrift. So nice, loads of questions coming through now. Of the APIs you listed, and you listed a bunch, what's your favorite and why? And are you aware of which API layer generally might have the best performance?
So I don't really have a favorite. They all work for different things. Understanding the JMX interface is a great tool to have in your toolkit. A lot of that information is available via Node Tool for different things. So Node Tool Ring looks at it and info and places like that. But there's a bunch of other information that's not available through Node Tool. You can get it using JMX Term or JConsole or other tools that allow you to get access to that. So understanding that really will put your Cassandra skills at the next level. Performance-wise and sort of implementation-wise, there are, as I said before, there are things on both that I like. The flexibility of Thrift can be very good. It can be great in some situations. It's a bit more efficient on disk. The abstractions that CQL3 brings along can improve your productivity. Performance-wise, I think they're both pretty much on a par themselves. They're within 5% or something like that, 5 or 10%, I would guess. I haven't seen any recent performance metrics. Nowadays, CQL3 has prepared statements, and the native binary driver has asynchronous requests and things. So performance-wise, I think it's so close it's not worth worrying about.
Great, and Timur is asking, is there anything like an execution plan similar to a relational database?
No, the best, well, kind of. There's a blog post on thelastpickle.com about query performance and execution plans and the read and write path, and there's certainly information on the DataStax documentation site about that. We don't have a pre-plan. We do have query tracing that came in version 1.2. You can find some information about that on the DataStax blog. And that shows you where a request goes through different stages and through different machines. It's a great tool for analyzing performance problems.
Thank you for that. And actually, there's another documentation question, so maybe hit this one as well, from Aaron. He's asking about documentation for data replication between two Cassandra clusters.
There is information on the DataStax doc site about replication between nodes, between clusters. To give you a brief overview, we send a space-efficient, a wire-efficient, one copy of data across the data centers. You want to look at things like the local quorum and the each quorum consistency level, but in general, it works the same as within one data center.
Okay, thank you for that. And question from Serg, do you see a possibility that Thrift will be deprecated?
No, there are no intentions to deprecate Thrift.
That's one of the beauties of the open source community. You know, as long as people want to use something, it stays around, which is great. James, describe the flow of events when a read comes in and you have, let's say, 1,000 SS tables on disk for a column family.
Cool. This will be a good one. So there are a couple of ways that we filter out the number of SS tables that we want to read. Everyone knows about the Bloom filters. These are our space-efficient probabilistic data structures that tell us whether the row we are interested in reading definitely does not or may exist in an SS table. We use that to filter that out. We also have the minimum and maximum row key, or actually the token, for each SS table, and that's in memory as part of our SS table metadata. We only go to SS tables where their min-max spans the row key that we're interested in. So we've eliminated that. So we filter with Bloom filters, we filter with the min-max key range. Then depending on the type of read, it depends on how we approach things. If you're reading by column name, the SS tables are ordered by their maximum timestamp, and in a progressive fashion, we read from SS table 1 and then 2 and then 3 until we've collected enough column values. So if we read that foo equals bar in the first SS table and we know that the next SS table has a timestamp less than the value we got for foo equals bar, we don't have to look any further because we know that the lower timestamp values won't override what we've got. If we're doing a slice where we're getting the first 10 columns, we have to go to all of the SS tables that we've got left and find out what their first column is for the row so that we know the first column in the collection. So there could be 3 SS tables that all contain the row, and we have to read the first column from all 3 so we know that bar comes before Baz and they both come before Foo.
Great, thank you for that. And, it sounds like a good topic for a blog post or maybe even a future webinar there. Ashok asks, what's the role of quorum within the context of the storage engine? How is the query result accuracy determined, especially with a large number of nodes?
So when we talked about our read callback, and I said we construct that with some information about the quorum, I kind of skipped over a few details there. We use quorum to filter, we use the quorum to understand how many of the nodes that we've got that are live endpoints for the row we need to go to. So if you're doing a read of CL2 with a replication, CL quorum with a replication factor of 3, we really only need to read from 2 nodes to get the quorum, and so most of the time we will only read from 2, even though there might be 3 nodes available. The times when we will read from 3 is when read repair is active on that request. By default, that's every 10%. That's 10% of the queries by random number generator. We then use that quorum when we're constructing our read callback, and he sits around and waits for that many results to come back. And then when you get to the response resolver, this is where we're dealing with accuracy of the results. So we're comparing the results from multiple nodes. If you're using CL1, we're only going to wait for 1 node to get your result back. The accuracy is eventually consistent accuracy. If you're using CL quorum, and you've used that for the write as well, then we've got our strong consistency because we can guarantee then that one of the nodes involved in the last write was also involved in this read, and because we choose the highest timestamp in the resolver, we'll always get that last written value.
Okay, great. And Doug asks, can you talk a little bit about tombstones? In particular, he would like to know if it's possible to minimize tombstones in CQL3 using row-level operations.
I don't think it's possible to minimize them. So tombstones are soft deletes, and we have soft deletes because we have a problem in this distributed database. If a node is down when a delete happens and the 2 other replicas do a hard delete, meaning they actually remove the value and remove any information that the delete happened, when the node that was down comes back up, the natural assumption is to say that the other nodes missed the insert, and so foo comes back to life again. So a tombstone is a soft delete marker that gets written. It's essentially an insert or an upsert. And that gives us time to get those soft delete markers distributed, and then during the read process, when we reconcile column values, the tombstones are dealt with. The way that you minimize the impact of tombstones, we can certainly do less deletes. We can do deletes at a row level rather than at the column level. We can use a lower GC grace seconds, which is the number of seconds before compaction may purge a tombstone off disk. The level compaction strategy, because it uses about twice the I/O as the size tiered compaction strategy, is able to purge tombstones a lot quicker. That's another approach. Particularly in the CQL3 world, if you're using the collection types, the set, the list, and the hash, there was a bug about this that got resolved in about version 1.25 or 2.6 from memory, but they were doing some things with tombstones that created lots of tombstones. They were doing range tombstones. So the best way to deal with tombstones might be to use level compaction strategy and a lower GC gray seconds, so long as your repair is being run.
Okay, great. And here's a question on security APIs, and just a little plug here for DataStax Enterprise. DataStax Enterprise does have advanced security in it. Aaron, here is the question for you. Are there any security APIs and implementations present, e.g. for authentication / authorization, and any plans around those as well?
Yes, certainly. They got a real improvement in version 1.2. So we now have roughly the equivalent of a SQL relational database security model. We have permissions on tables, we have users, and all that sort of stuff, alter and delete and select. It's essentially now disabled by default. If you go to the DataStax documentation site and you look at version 1.2, you'll find information in there. It's managed with CQL statements that are similar to SQL statements in the DDL range of add user, allow, and deny. I don't think we have deny, sorry, allow, and things like that.
Okay, thank you. Gavin asks, is it possible to provide a JDBC compliant abstraction for the native protocol?
Ooh, this is probably more a DataStax engineer question. So the native protocol, we have implementations in Java, C#, Python, and C++. At least the Python one, it steps outside of the database container that they have there. I'm not sure on the Java implementation whether that is JDBC compliant. You would have to go and have a look. If you look at the DataStax organization on GitHub, you will find their Java driver there. In the README at the top of that project, it has how to ask questions. They have Google Groups and IRC, or the documentation might already cover it.
Okay, and any other questions you want to ask, please keep them coming. We've got just a few minutes left. I'm not sure I understand this question, but I'll ask it anyway, Aaron. How does the Dynamo level locate nodes which store a specific key?
Good question. This is our consistent hashing algorithm. So I skipped over the DHT, the distributed hash table, and the locator package. If you look on my website, in the speaking section, you'll see a couple of talks I've done. The In Case of Emergency Break Glass talk I did at the Cassandra conference in June, and I'm doing next week, has a very brief introduction about how we do this. There's some other talks on there called things like Cassandra Does What, and an introduction to Cassandra that I've done here a few months ago. We talk about that. Briefly, we take your row key and we hash it into a token, and we assign, that token has a very big value range. We assign small ranges of that token range to each node, and we consider that. We call it the primary replica, just because we don't have a better way to describe it. That's what our token and partitioner does. Our locator things, the snitch and the replication strategy, use that information. So we take our row key, find the token range that contains it, find the node that's the primary for that token range, then use the strategy and the replication strategy to select the other nodes that we want to go to. So it's a very quick overview, but I encourage you to have a look on thelastpickle.com in the speaking section.
And another question, could you please explain the best way to implement or use row-level caching? And this may well be our last question. So
row-level caching, for those that don't know, we have a row-level cache. By default now it sits outside of the Java JVM, and it does what you'd expect it to do. If you're doing a read and we have it in the cache, then we read from cache and we don't have to touch disk at all. There are a couple of anti-patterns in there to be aware of. The cache is an invalidating cache, which means that when you do a write, we blast the previous one out of the cache, we don't update it. There's another cache implementation, which is an on-heap, on-JVM heap implementation that is a write-through cache, but the default is the off-heap. The other anti-pattern is that when we get a cache miss, we have to go and read the entire row from disk. So if you often read one column from a row, that might not be a great implement, and it updates frequently, or at some level of frequency. That might not be a great candidate for the row cache, because the updates will blast it out of the cache, and whenever we do a read, we have to go and read the entire row to fill the cache. So it's a good idea to use it on things that don't change too frequently, that you might read a lot. That could be something like user details, you know, mapping from their login to the display name you want to give them or something like that. That's not going to change too frequently, and there's not going to be a very wide row you'd expect. So they're the best ways to use the row cache.
Okay, one more, Aaron, if you're up for it. We'll make this a quick one. Do mem tables also have Bloom filters, or is it only for SS tables?
It's only for SS tables, because the number of mem tables in memory is normally 1, sometimes 2. If there's, you know, 1 in the flush queue, if the flush queue is full, maybe there's a couple more, but it's still only a few. Whereas on disk, we could have tens of SS tables, and if we're using level compaction, more than tens.
Okay, well, Aaron, as always, thank you very much for taking the time today. You are back next week on the 29th. Is that next week? I guess it is, isn't it? Yeah, the 29th. Join Aaron, where he is going to be presenting In Case of Emergency, Break Glass, which was a really well-attended and really well-reviewed presentation from the Bay Area Cassandra Summit. So make sure not to miss that one. And Aaron, thank you very much. We always appreciate having you here.
Thanks, Christian.